All right, Math 2, here we go. We got 7-1, dividing radicals. Put your name and your period on your paper. So our question today that we need to answer is how can we get the radical out of the denominator for problems like this where we got 6 divided by root 3? Because we're going to be finding out that we shouldn't be leaving radicals in the denominator. So we need to figure out a way to get them out of there. So explain how you can do that. By the end of this section, hopefully you'll know how to do this. And so as a summary, just at the very end, answer this question. All right, so to review, square root of 20, what does that mean? Well, if I have the square root of 20, that is saying what number multiplied by itself will equal 20. So what number can't spell self for some reason, equals 20. So square root is just the opposite of squaring. It's the opposite operation of squaring. So we would say, well, it's not a perfect square. Root 16, that number multiplied by itself would be 4, because 4 times 4 would be 16. So I've got root 16, we know is 4, because what number multiplied by itself is 16? 4 multiplied by itself is 16. And then if I take 25, what number multiplied by itself is 25? Well, we know that's 5. So I've got root 16, root 20, or root 25. Root 20 is somewhere in between those. So we should say, oh, it's going to be 4 point something. Okay, so and we were talking about in the last unit, well, how do we simplify these types of problems? Because we talked about when they weren't perfect squares, like root 20, that they go forever. It's kind of like pi. These numbers will go on and on and on and on forever, never repeat themselves, and you can't write down the actual number, which is why we use the radical. Because if you want to write down the specific number, you can't do it just by writing with decimals. So we just leave them in radical form so that it's the exact number. So we talked about how we could simplify some of these. And we said earlier that what we want to do is we want to get all of the perfect squares out of here by finding factors. So what multiplies to give me 75? Because that's what a factor is, something that's being multiplied. Well, I know that's 3 and 25, right? Because if you have 75 cents, that's 3/4. So, and then 25 I know is 5 times 5. That's my perfect square. So I got a pair of 5s there. So the square root of 25 is 5 because it's 5 times 5. So to simplify it, we said, oh, we can take the 5 outside and then the 3 would stay inside the radical. And we talked about how it's kind of like Friday night. Couples get to go out and singles, they have to stay home. Ba-dum-boom. All right, so the next one, this one has a coefficient of 5. So anything that I take outside of the root, we're going to have to multiply by 5 because this says 5 times root 24. Well, 24 I know is 4 times 6, and there's my pair. I've got 2 times 2, and then 6 was 2 times 3. So I've got these singles left over. The 2 will come out and multiply by the 5. And then inside, we'd get 2 and the 3. Remember, these are all factors. They're all multiples of each other. So if I have multiples or multiple factors left over, I just multiply them and leave them inside. So this one finally gives us 5 times 2 as the coefficient, so that's 10. And then in the radicand, the numbers here, 2 times 3, gives us 6. So that would simplify to 10 root 6. So we want to take out all the perfect squares possible. Now, what about decimals? Is it possible to do it with decimals? Well, I know that 36 is a perfect square. Okay, so this is 6 times 6, but this is 0.36. So what would I multiply the 6 and 6? What would the 6 and 6 be as decimals to get 2 decimal places? Well, remember when you multiply with decimals, you multiply the numbers and then just add up the number of decimal places. So since this one has 2 decimal places, here I know that each of these had 1 decimal place. So 0.6 times 0.6 is 0.36. So this even works with decimals, where we could get 0.6 is the answer for that one. Same thing for this one. I noticed that 144 is a perfect square. So that's 12 times 12. But here there are 1, 2, 3, 4 decimal places. So I can't just do 12 times 12 because that'd be 144, not 0.0144. So if I gave this one 2 decimal places and this one 2 decimal places, now I've got 1, 2, 3, 4 decimal places. That's why this answer has 1, 2, 3, 4 decimal places. So I've got a pair there of 0.12s. So this would just be 0.12. So just look for the perfect square there, and then ask yourself how many decimal places do they need to have in order to give you the decimal places that are right there. All right, so that is simplifying. We already did that way at the beginning of the semester. Now we're going to divide radicals. There's a lot of different things that you can do with dividing radicals, but you cannot end a problem with a radical in the denominator. So at the end of the problem, there should not be a radical on the bottom. The other thing that we know is that a radical of a fraction can be split up into 2 separate radicals. So root A over root B is root A over B. So I can go backwards and forwards using this if I needed to. Now, what we found out earlier in the year is that radicals multiplied with other radicals. Well, radicals also divide with other radicals. So if you've got a radical here and a radical there, I can, according to this, I can rewrite that, or at least look at it, as if I've got 35 over 28, right? So I can go backwards and forwards with this rule. So what I want to look at here is, can I reduce the fraction? So the fraction has 35 and 28. Does any number go into 35 and 28? Yep, 7 does. So this one would become 5. And this one would become 4. So this becomes the square root of 5 over 4. But I still have a radical in the denominator because this is in the radical. So let's split these up real quick. So this is root 5. You don't have to do all these steps that I'm doing. I'm just kind of trying to show my work here. I mean, you could have just started reducing them right here if you wanted to. And probably if I weren't showing this to you for the first time, that's what I would have done. But anyways, so I got root 5 over root 4, not allowed to have a radical in the denominator. That's our first rule up here. But the square root of 4 is 2. So my final answer is root 5 over 2. Now we can write this like this, or we can realize that this is 1 times root 5. So there's a 1 out there that I can't see. So I can write it like that, or I can say it's half of root 5. So those are equivalent. They're the same thing. So I can say my answer is root 5 over 2, or half of root 5. All right, next one. Okay, so we said before we can reduce the fractions like we normally would. So I see that 2 goes into this once, 2 goes into this 16 times, and I'm left with the square root of 1 over the square root of 16. Those are both perfect squares. The square root of 1 is 1, square root of 16 is 4. I'm following all my rules. I don't have a radical in the denominator, so I can stop my answer at that point. All right, they don't always nicely get out of the denominator like these two problems have. Sometimes we have to do a little bit of work to get our radicals out of the denominator. So when we have to do that, we call it rationalizing the denominator. And here's what we're going to do. We're going to multiply the numerator and the denominator by the same radical. And that's how we're going to get rid of the radical in the denominator. So here, my radical is root 3. So I'm going to multiply the numerator and the denominator by the same radical. So I'm going to multiply the numerator by root 3, and I'm going to multiply the denominator by root 3. Why is this okay to do? Because I'm multiplying by the number 1. That looked really bad. It was supposed to be like really pretty, and you're supposed to go, oh, I want to do that. Yeah. Anyways. So that's root 3 over root 3. That's just 1, right? And our multiplicative identity says that if I multiply by 1, the number stays the same. So this is okay. It's totally all right. All right, so 2 times root 3 is 2 root 3. Root 3 times root 3 is root 9. Okay, so why was multiplying by root 3 over root 3 helpful? Because root 9 is 3. And now the radical is out of the denominator. Now, anytime you multiply a radical by itself, look what happens. The radicals go away. Why did it happen? Because we just squared root 3. This is root 3 times itself. And squaring is the opposite of square rooting. So if I square these numbers, it just takes away the root, and I get 3 over here. I don't need to do the 9 here. Root 3 times root 3 would be 3. Root 10 times root 10 is 10. Root 1,000 times root 1,000 is 1,000. Any root times itself is just the number that's inside the root. So remember, we could have also written this as 2/3 of root 3. All right, let's get to this next problem. Don't like the radical in the denominator. So what am I going to do? I'm going to multiply the top and the bottom by root 2, which is just multiplying by the number 1. So in the numerator, 4 times root 2 is 4 root 2. In the denominator, this is 3 times root 2 times root 2. Remember, root 2 times root 2 is 2. So here I get 3 times 2, because root 2 times root 2 is just 2. So this becomes 6 root 2. Why did I say 6? That's the bottom. It should be 4 root 2 over 6. Now, I still can reduce these numbers over here. So whole numbers can reduce the whole numbers. Radicals only reduce with radicals. The 6 cannot reduce with this 2, because this one's a radical and this one's a whole number. So we can only do these 2. So I would reduce them. 2 goes into that twice, and it goes into this one 3 times. So I end up with 2 root 2 over 3. Or 2/3 of root 3. Root 2. Why did I say root 3? I don't know. Long day. All right, next one. There are so many different ways to do this one. Let's say that you just go, okay, I'm going to multiply by root 12. Go for it. Root 12. Root 12. This would give you 5 root 36. And then root 12 times root 12 is 12. Wait a second. Root 36 is 6. So this is 5 times 6. Sorry, over 12. So this gives me 30 over 12. Wait a second, that reduces. 6 goes into 12 twice. 6 goes into 30 5 times. My final answer is 5/2. Could I have done it another way? Yes, you could have. You could have just said, okay, this is 5 root 3 over root 12. These two are radicals. You can reduce a radical with itself. There's 1, 4. 3 over 12 reduces to 1 over 4. So I get 5 root 1 over root 4. Root 1 is 1, so I get 5 times 1. And root 4 is 2. I get the same answer. A little bit quicker that way. Is there another way to do it? Yes, there is. If I had 5 root 3 over 12, root 12, you might say, well, can I just reduce this into 4 times 3? And then this one would be 2 times 2. Yes, you could do that. So this would become 5 root 3 over 2 root 3. And then the root 3's reduce. And you get 5 over 2. So many different ways to do it. You could have just multiplied by root 3 over root 3 on both sides if you wanted to. You could have done it a lot of different ways. As long as you're using the properties of math correctly, you can be creative in how you solve these problems. There are multiple ways to get to the end. There's only one right answer, but there's multiple ways to get there. All right, so make sure that you write your summary at this point. Remember, your summary was, how can you get the root 3 out of the radical? You should know now, right? So, and be able to explain that. That's all I got. Math hard. See you next time.